Hey, Physics 20s, believe it or not, we are already on the next unit. We're in Unit 5, which is all about circular motion. Um, That's not the right size felt pen. It's a little better. All about circular motion. So if you haven't already got this workbook, remember it's available online. Or if you really need, you can contact me or your assistant principal and come into the school and get one. But it is on our Google Classroom in the classwork section, and then scroll down to the, well, Unit 5 part of that classwork section. Now, you might be thinking to yourself, circular motion. Why are we studying things that's circular? Well, it's motion and it's in circles, and it's actually a bigger part of your life than you would imagine. And you'll see that as we go through this unit. So one thing that we kind of want to think about, and today I should also mention, today we're focusing on the kinematics of circular motion. So how do you know when something is accelerating? This is the very, very first question. Well, there's two ways that things accelerate, right? Well, there's the change in velocity. I mean, that is how things accelerate, is there's a change in velocity, but there's two ways to change velocity. There's a change in magnitude, and there's a change in direction. So up until this point, we've talked about a change in magnitude, things speeding up or slowing down, and that is our acceleration. But we could also have a change in direction. So again, change in magnitude, things slowing down, things speeding up. Change in direction doesn't necessarily actually mean that it's speeding up or slowing down whatsoever. So when we talk about acceleration that is always perpendicular to the velocity, because it's 90 degrees to the velocity, it doesn't speed it up or slow it down. It only deflects it. So it only changes its direction. We call this centripetal acceleration, or sometimes you'll hear people say centripetal acceleration. So it's center-seeking acceleration. Acceleration always towards the center of the circle. Cool. So we see this, again, all over the place. You're sitting on a Ferris wheel. You've got centripetal acceleration. You've got a change in velocity, but not in direction. You're sitting on whatever this thing's called. Absolutely. You're driving in your car and you go through the bottom of a dip or over the top of a dip. Absolutely. You've got it. You're driving in your car and you go around a circle. Perfect. No problem. You are cruising around the velodrome. You've got it. So anytime that you move in circular motion, these are the ideas that we want to talk about. So as we go through, the first formula that we kind of want to build here is speed. So speed, speed, speed. So here we have this thing moving around in a circular motion. Its velocity, notice I'm putting an arrow over the top, is always perpendicular to the motion, but its speed is how quickly it's going around in the circle, right? So speed, no direction, velocity, direction. Now, the speed, and we're dealing with uniform, by the way, so speed is not changing. Velocity is constantly changing, but speed is not changing. And if speed's not changing, we're dealing with v is equal to d over t. Any ideas, though, how I could get a distance out of this? Oh, yeah, it's a circle, right? So an easy distance to deal with is the circumference of the circle, which we remember back to math whatever, is 2 pi r. Now the t is not just any t. It's a very, very specific one. We're going to call it capital T. We're going to call that period. And the period by definition, so it's measured in seconds, period by definition is the amount of time that it takes to do one lap around the circle, or one complete rotation around the circle. So time for one rotation, right? And then this is our circumference, which is realistically one rotation. Nice, so we can get the speed there, right? V is equal to d over t, but a very specific d, the circumference, and a very specific t, the period. Cool, okay. So velocity, we already kind of talked about this one on the last slide, but velocity, if you were to take a freeze frame, so pretend you're whipping this thing around in a circle, the ball's here, it's on a rod, and you're whipping it around in a circle over and over and over and over again. Let's just get rid of that to clean it up. right? You can think about this. It is always at a tangent to the circle. So remember, tangent means just barely touching it at one point. And you could think about it as the inertial pathway. So where it would go if you were to let go of, say, the string that you're whipping it around on, right? You can think about this as mud flying off your bike tires. You could think about this as rock slings from David and Goliath or whatever that thing is. I don't actually remember that well. You could even just try this out in your house, right? And I would recommend tie like a little mass to the end of a string and try letting it go at different places. So if you're spinning it around this way, and if you let it go right at the side, it's going to go straight down into the ground. If you were to let it go right here, it should go straight up into the air. If you were to let it go right at the bottom, it should go straight to the side, and of course it would go into that parabolic motion and become a projectile, but it always is a tangent to the circle, so velocity tangent to the circle. And again, the example is the discus. So this person is making that little discus fly. They want to let go of it off to the side here, so it comes, I guess, directly out of the page at you, which is a terrifying thought there. So at a tangent to the circle. Okay, so we've talked about period. Period, remember, is the time it takes for one rotation. Okay, what if we had 850 RPMs? What's a RPM? If you're saying rotation per minute, you are bang on. Cool. So 850 rotations per minute, and I'm looking for the period. That's the time it takes for one rotation. We've actually got, right on your data sheet, you've got period, and this is kind of handy. Period is the total time, and I think it says over the total number of cycles. And rotation, cycles, sort of the same thing. So essentially what I'd look at is, one, I want to convert this to seconds. So I'm going to say time is equal to, well, rotations per minute. 1 minute is 60 seconds. And the total number of rotations in that time is 850. I would divide that out. I'd get my calculator, try and turn it on. I do 60 divided by 850. And I'd end up with a period of, 0.706. Cool. All right, so that's not so bad. How to get our speed formula. I think we've already talked about this. I might have jumped the gun on that one. So, a centrifuge. Here's our first example. A centrifuge, that's a thing that essentially spins really fast to separate different components. You often see them with blood. So blood centrifuge separates the plasma from the platelets, from the red and white blood cells. Check it out if you haven't seen it. It's realistically a device that you've got test tubes, and they just spin around really fast, and the most dense, heaviest stuff sinks to the end. The least dense stuff goes more towards the top. That's a terrible picture, but check it out if you've never seen one before. Okay, and back to my other felt pen. Cool. So we got a centrifuge spinning at 3,600 RPMs. If the speed of the test tube at the end is 85 meters per second, we want to determine the diameter. Cool. Okay, so let's go through. First thing is RPMs. I probably want to change that into period. So that's 60 seconds for every 3,600 cycles. Let's see. I feel like I should be able to do that one in my head, but I'm going to do a calculator. So 60 divided by 3,600. There we go. 0.0166667 seconds. So there's the period, the amount of time it takes for one cycle. Not a lot of time for it to go around once. Next thing, I got V is 2 pi r over the period. I'm looking for the diameter. So some mathy people out there, you might just say, oh, well, it's just pi d instead of 2 pi r. Pi times the diameter. Let's go through. This is the way that it's written on our data booklet, so I think we'll use this one. Let me just rearrange. I want radius is going to be equal to speed times the period divided by 2 pi. So the speed is 85 meters per second times the period, 0.01666, whole bunch of those, and then a 7. And then we're going to divide that by 2 and also divide that by pi. Please don't put 3.14 for pi. There's a button on your calculator. Actually push the pi button. So let's have a look. So I got 85 times my answer divided by 2 and also divided by pi. So pi is second function and directly above the dividing sign. So I hit enter on that one, and my radius is going to be equal to 22.5 centimeters, yes, or 0.225 meters, which means my diameter is just going to be twice as much. So diameter is equal to 45 centimeters or 0.450 meters. I'm going to double check that because I'm pretty tired. Times 2. Good. 45 centimeters. Awesome. Okay. That kind of makes sense. Like when we look at this person's hand over here, and I think from here to here is probably the centrifuge, that makes sense, right? These centrifuges are not huge. Okay, next piece we want to look at is the centripetal acceleration. So how do we actually measure that acceleration? Remember, it is always towards the center of the circle. It has to be perpendicular to the velocity and has to be towards the center of the circle. Why does it have to be perpendicular and towards the center of the circle? Well, if any component, so if we were to break this one into components, if any component of that acceleration is in the same plane as the velocity, it's going to slow down and we'll be changing the speed. In this case, slow down. If it was this way, it would be speed up, but it would still change the speed. We're focusing on keeping that speed constant, so it needs to be 90 degrees in order to do that. Cool. So our equation for this is very simply AC is equal to v squared over r, where v is the speed in meters per second, r is the radius in meters, and the units work out to be meters per second squared. If you want a bit of a challenge, you can go ahead and see how the units from this turn into our regular acceleration. Cool. There's actually, though, one more formula. So I'm going a little out of order here. Actually, one more formula for this based on the fact that we know what speed is. So AC is equal to v squared over r, but I know that v is 2 pi r over t. So if we were to expand on this, right, I'd say AC is equal to 2 pi r over t, but this whole thing is squared. And then of course that is, I'm just going to do times 1 over r rather than dividing by r. So I can simplify this. This is 4 pi squared r squared over t squared times 1 over r, or in other words, divided by r. We see one of the radius cancels, and we have AC, our new formula, 4 pi squared r over t squared. Cool. Now that being said, I just kind of rushed through that, how we build this new formula. If you don't know how to build this new formula, that's okay. Check out your data sheet. See if you can find this, and the last one for that matter, on your data sheet, but 2 formulas. So when you're given a question that deals with the speed, obviously use this formula. When you're given a question that deals more with the period or the time for one lap, you're obviously going to use this formula. So you got choices here. Choices. Cool. One thing that I'll get you to put the video on pause and do, can you figure out the velocity and acceleration vectors for this particular motion? Put it on pause, go ahead and do that right now. Alrighty, so the speed is going, it looks like this thing's going around this way, so that means my velocity has to be perpendicular, not perpendicular, sorry, tangent to the circle, and my acceleration has to be 90 degrees and towards the center of the circle. So if you drew that or you thought that, perfect, you're on the right track. Okay, second example to check out. We got centripetal acceleration of 12 meters per second. If the speed is tripled and the radius is doubled, what is the new AC? Okay, cool. So we're dealing with speed and we're dealing with radius. So I think I'm going to use this version. AC is equal to v squared over r. Nice. Then I go through and I say, okay, the speed is tripled. So I'm multiplying the speed by 3. Cool. Can I simplify this? Because I got 3v and the whole thing is squared. So I'm multiplying it speed by 3 and then I'm squaring. I can simplify this and I can say, oh, well, that's 9 times v squared. Oh, so what did I just do to this side of the equation? Well, I multiplied it by 9. What do I need to do to the other side? Multiply by 9. Cool. Now it says the radius is doubled, so I'm going to put 2 times the radius. Might as well do it in both places over here as well. So I just put a 2 by the radius, multiply the radius by 2. But what did I do to this side of the equation? I divided it by 2. What do I need to do to this side? Divide by 2. So my new acceleration is going to be equal to 9 over 2 times my old acceleration, which was 12 meters per second squared. So if I were to plug this into my calculator, I would simply do that, not that, 9 divided by 2 times 12, and it works out to be 54 meters per second squared. Cool, we've done some proportionality work before. It's a little bit trickier with the squared part, but remember you are multiplying the speed by 3 first, and then the whole thing is being squared, which we can simplify. Cool, so that is, I believe, it for this lesson. It's a bit of a short one, which is nice, but please make sure that you understand the ideas from this lesson, because the next one, guess what, is building off of this one when we talk about centripetal force. And you know that force is very closely related, so we need to know that. Anyways, that is it for now. We'll talk to you later, Physics 20s. Bye-bye.